Okay, I think we're ready to start. Hello, everyone. I'm going to talk a bit about what I'm doing for my PhD, which is modeling of attention, of auditory attention. And you can start with the question of what is attention, right? Attention helps you filter out or filter the relevant information, filter out the irrelevant information, and only focus on of all the information that you get from your senses. You can only focus on what is relevant right now for maybe the task that you're doing or what is interesting to you at this moment. It depends on both the bottom-up factors, such as characteristics of the sound itself, but also on top-down mechanisms which are related to, maybe a task that you're doing right now, or your particular interests or your experience. And why would you want to model auditory attention? Well, if you know. So what I'm actually interested in most is the bottom-up part. So what makes the sound salient, what makes it interesting for people, what makes people pay attention to it. If you know that, you can use it to, say, design sounds that will grab people's attention, which is useful for interfaces, is useful for alarm sounds. It can be useful for broadcast situations where if you maybe are trying to optimize broadcast, if you know which sounds people will find more interesting or naturally pay attention to, you can use that. If you are building a machine listening module, you can use that as well. Teach a computer to listen the way humans do. That's what you're interested in. People have been trying to model auditory attention for not that long, actually, but maybe 10, 15 years. A classic Saliency Map created by Kaiser, and others was basically a Saliency Map that was used in vision for static images applied to a spectrogram. And this was a very simple solution, but it didn't take into account the properties of sound and the things that make sound different from images, such as its temporal structure, the fact that it builds up over time. Also, a spectrogram doesn't have any phase information, and you can miss some information because of that. But it kind of became this basis for other people to work on, and some researchers tried adapting that salience map for sound, adding more sound relevant features, or biologically inspired kind of parts that were directly related to how humans hear. Others tried using the approach that I actually like is using some signal statistics, and particularly the one I really liked was a model that used predictive coding in the form of a Kalman filter that you might have heard from me about because I talked about it a lot. So I will talk about that a bit more in a moment. But one thing that all of these models had in common was that they all only looked at one-channel signals. So none of them really took any spatial information into account, which I thought was could still provide some more information. It could be important whether the sound is coming from your right or your left or front, or is it from the back, or is it moving in space? Is it static? So on. Okay, so I want to talk about the Kalman filter a bit. Okay, let's open this slide and just want to say why I think. Well, what it is, it's what Kalman filter does. It predicts, it estimates state of a process based on some noisy measurements. So if you have a process with that you can measure, but the measurements are very noisy, you can't really trust each of your measurements to be correct, exactly correct. So what Kalman filter does is it kind of filters out the noise in your measurements based on some information that you have about the system, and also the previous measurements that it got. The nice thing about it is that it doesn't actually store any previous measurements, because it just updates its internal model, so you don't have to store a lot of previous samples. You just need this one measurement. And it is recursive. Do I actually have any pointers? I don't. Anyway, so at first it predicts based on the information that you have about the system, and based on its previous estimates, previous predictions. It predicts the current sample, what it should be according to it. Then you get the actual measurement from your system, and based on this previous prediction, you kind of correct the previous prediction based on this measurement. So an example that is not related to acoustics or sound in any way, but is found in a few places. It is kind of a, I think it is actually, Kalman filters are used for that. It's kind of an autonomous robot that just moving around. It has some information about where it is based on GPS data, but the GPS data isn't very accurate, and maybe it isn't precise enough. But it also knows that, it was planning to go straight, and it was planning to go at a certain speed. It can't be sure that it reached the point, because maybe it hit a wall, or maybe, some other obstacle was there. But it gets the GPS kind of measurement of where it is, where the measurement says it is. It kind of combines it with its knowledge about where it was going, and based on that, it assumes, okay, so based on these two, I think I am actually here, and then continues on and on. So why this for attention? Well, we can say that in general, things that grab your attention are things that are not expected, things that are surprising, things that if something changes in a way that you weren't expecting, it grabs your attention. So basically what we do is we run these Kalman filters, which I will go into a bit more detail of how it works in the model, but basically you run them on some feature vectors, and if the feature vector changes, you kind of try to predict each next sample of the feature vector, and if it changes in a way that you didn't expect, if it doesn't fit your model, there's a huge difference, then that's surprising, and that's unexpected, and that's where you might have something that will grab attention. Okay. So yeah, our model is based on this Kalman filter, which is based on this model from these guys. But unlike this model, it will take spatial location of sound into account, and it will work on objects. What is the general structure of the model? As input to the model, we'll have sound objects with some metadata, like location of the sound and how it changes over time. So for the object-based audio people, this should look familiar. I don't know if any one of them are here. But then from each of these objects, you extract feature vectors. At the moment, the model, I've coded the Kalman, the tracking part of the system, which I'll show you in a bit. But this hasn't been done yet. So at the moment, what the actual input to the model is just feature vectors and location that changes over time. And this is for each object. In the future, or this probably won't be my PhD, but someone could potentially add maybe module that kind of does some stream segregation and localization, and you could actually have 2-channel or more channel audio and kind of extract objects and say what people are listening to, paying attention to in the scene. So starting with these feature vectors, you run the Kalman kind of tracking module on each of these features. And I'll show you a bit more about the Kalman tracking later. And from each of these modules, you get kind of a score. Let's call it a saliency score for each feature. So feature 1, 2, 3, different colors. Then you will have to assign different weighting to different features, because this might be maybe loudness, maybe some spectral centroid, maybe actually location of the sound. Maybe it's like moving in a weird way like this, and they will have to be normalized, because not all of them are equally will be equally important. So this will be obtained hopefully from experimental data, the weights, and after that you will combine all of these scores for features into one kind of saliency score over time for each object. So it kind of you wouldn't pay attention to it here, but maybe at this point something changes about it and you will notice it. Okay, so let's go into that deviance detection Kalman part. So this works on feature vectors again. It actually doesn't just use one Kalman filter, it uses multiple Kalman filters for each feature. So at first you will do some clustering to determine how many filters to start with. And this just shows one, but I will show you later an example of where there's more than one. But imagine this is just a feature vector. Maybe it's very quiet, and then it goes louder, and it's loud. Once you determine, so we found only one filter that we want to start running. Then, why is my battery running low? Okay, sorry. So then you run this Kalman filter. So these circles will be like prediction of the filter. So you can see that the filter kind of has learned, based on a little frame here, has learned what this feature, how this feature changes, and it kind of predicts it to be still the same, because it hasn't changed. It wasn't changing before. So nothing's happening, basically. Then, at this point, the filter will still predict it, the new kind of frame to be here, but it has actually started changing. So this will be a point where you'll get the surprise kind of saliency score. You will also, after that, you will also start a new filter that will be able to track this bit. And if there's no, if the filter doesn't doesn't get any data points for a bit, you just close it, kill it, because you don't want them running forever for computational reasons. And also because it's kind of like a memory. So for a bit, you can keep it going, but then you kind of, like, people will forget that something was happening in this area. It should also forget. So in this case, you get one peak here, because this change, I think it will actually be shifted in the actual implementation so that you get a peak in the right place, and then a peak here where there is another shift. So a few examples. These are just simulated feature vectors. I don't actually have real feature vectors. Sorry about that. But this is the example that we've shown before. This shows how different filters run and the detection score, or the deviance score. So you can see that if the slope there is quite high, it will detect these two as kind of salient events. But if you make the slope low enough, the filter will just adapt to it, so you won't get any scores. So if the changes are slow enough, the filter adapts to them. Another example, there's like an anomaly in the there's some odd, what do you call them? Outlier maybe in the feature. You get a spike there. And this example shows why it actually, what's the benefit of actually having two or more filters running at the same time. So here, you kind of have like a pattern, maybe could be, say, frequency, kind of like a siren maybe pattern or something, and then one outlier out there, which is a different frequency than all the other that pattern. So when you do this clustering at the beginning, which actually is why there's nothing here, because this is needed for the clustering, the algorithm finds two kind of two places where it should run the filters, and it tracks this stream and this stream, and then it gets this outlier, and you get a spike here. You get a spike here as well because this is how long, in this case, the memory was, and so it forgot this one before it started again. The memory is again something that how long it should be. It will probably be determined. If it was just one filter, it can't adapt to this pattern because the model of how the features change is too simple. It basically is just linear. So it will check what the difference was between these two points, and will expect the next one to be somewhere here. But that's not how it worked. Okay, so back to the general model structure. Output of the model. You want to have the score for each object, and you want to kind of draw it on a map, but not necessarily. So this is the classic saliency map that I talked to you about at the beginning, which is actually it's run on a spectrogram. So the output is like a spectrotemporal map, time versus frequency. But what I would like to have is an actual map that includes, location. So not this, but something like that. So you have your just horizontal location around the listener, and you have time because obviously it's sound, so it changes over time, and that's important. And then so maybe you have one object and these are different objects. So maybe you have one that starts here almost in the middle and then kind of turns right, maybe this one is more bright, so this was actually more salient than the others. These are maybe a bit louder, wider. Yeah. This one maybe it's the same and kind of jumps in a weird way, something like this. Okay. So how do we actually don't want that. How do we actually include the spatial information in the map? Well, one way is one simple way is just to have, if we knew that certain locations are inherently more salient than other locations. Maybe sounds coming from the front will grab your attention all the time. Then we can just apply a simple weighting to the map. We could also treat location over time as a feature, just like all the other. We could have some more, some fancy location-related feature vectors, such as maybe feature location, some kind of contrast. So maybe something that, well, yeah, just haven't really researched this yet, but just is something maybe that something that appears suddenly, like in this spot. Maybe this will be salient, and this might be salient because it's moving, as opposed to the static sounds. But the problem with this, well, all of this, is that there hasn't really been much research or any research done on how the location of sound actually influences saliency and attention. So this is where what we're trying to find out with some experiments. Our first experiment last year was designed to do that. You had some of you have taken part in this. You had two streams of noise bursts, and one of them had kind of a change that you would try to detect, but they were both playing at the same time, so it's kind of difficult. You probably default to listening to one of them rather than the other. One was high frequency noise, one was low frequency noise. And the assumption was that if there's any location that's inherently more salient, then you will default to that location more often, and be better at detecting these changes in the patterns. So what we measured the response times and accuracy, and the results seem to be that for all the sounds, there wasn't any difference for location. However, there was a difference only for the high frequency noise. There was so this is the high frequency noise. There was this back location was significantly different from the front, so people were significantly slower at the front than they were at the slower at the back than they were at the front. There's no significant effect here for the low frequency. So one thing that was a bit of a problem with this experiment was the noise bursts, because they were not very natural and they were not very pleasant. So for the next experiment, we tried to make it more natural and ecologically valid. So this, I've been wondering how much to talk about this experiment. Big. And I think I will not talk too much, just in case I want to run something very similar again on some of you. But in general, it was a more natural kind of experiment. People were sitting in the middle of a room, and maybe this is already too much. I think actually too late. It's too late. So. and there were sounds. Yeah, well, too late. You can't unsee this. So they were. They're sitting in the room. They were played some natural sound scenes, more or less natural. And I asked them to, some of you, to track your attention or where you think you're listening with the joystick. So kind of in a kind of the most natural situation, with no suggestions of what you should or shouldn't be listening. And there were sounds in the kind of, call it the background, but it was really more like a distraction thing, which was for one case it was speech, and for the other it was like a natural background with sound events. And on top of that, we had our target sounds, which were in these gray locations. So kind of you had I asked to, so if you only had the okay, let's go to the next slide maybe. If you only had the target sounds, people were able, you were able to follow them very well. And this is actually, so this is the event, the red, and the joystick. You can see that it follows it very well. But in the actual in the actual main experiment, you had lots of distractions around. So they were sometimes in a different location. There were sometimes they were in the same location. But we were not. But what we want to find out is people's responses to these target sounds. So what we would want to get from what we have right now from the experiment is basically this, which is we know where the events were, and we know where the joystick went relative to where the events were. What we would like to find out is for each of these events. So sorry, 1, 2, 3, 4 are different areas. So I don't remember which one is which, but say 1, 2, 3, 4. So if in this case, event was in area 4 and joystick goes to area 4, was in area 1 and goes to area 1. In this case, there's an event here in area 4, and the joystick kind of goes there, but it kind of goes back to 1, back to 4 again, and then there's some points where you can see that person wasn't interested in this sound at all, because it just went to 4 directly. And we would like to get some hit-miss score from this. And if anyone has any suggestions, that would be great. It will probably be some kind of a window, time window, and whether the joystick went to that area within the time window or not. That would be a hit, and if not, it would be a miss. And we'll see if there's any differences between front, back, left, right locations. Okay. So there might be, what's next? Might be some follow-ups now. I told you so much. I don't know if there will be follow-ups, but maybe. To this experiment, there were some issues with localization, so I might actually get more people to just do task without distractions, just to see if people are able to actually localize. This was reproduced in ambisonics, so there are some front and back confusions that might be an issue here, but but we'll see. And after we get enough data, we'll hope to go on with the model and kind of have an actual spatial model, and also with the feature extraction part. And it would be, I think, also interesting to, because I didn't talk about it in the end, but one issue with the experiment about auditory attention is that there are many different methods that people use, and there isn't one that everyone agrees is the standard. So basically, everyone uses, their own method and says it's saliency. So some people just ask people to rate what is interesting and what isn't interesting. Distraction experiments are common. So I was thinking maybe next one will be kind of a distraction experiment to see if we can get the same result from all these three experiments. Okay, yeah, that's it. Any questions?